One thing we want to point out before we start looking at the functions themselves as logarithms, logarithmic functions, we have to define what's called a common log. A common logarithm is any log with base 10. When you operate on most calculators and you take a logarithm, it's doing it with base 10 as its consideration. So if you see or you type into a calculator log, oops, let's try that again. You type into your calculator log, and you're going to do that of some number 3, you're going to get some decimal equivalent. So I'll demonstrate. If you have a graphing calculator, go check it out. Log button, hit the log button, type in 3, you're going to get 0.477. So what does this mean? It means that our base now, when there's nothing written in our subscript, it's automatically, common logarithm is log base 10. And all logarithms that are just written log, like log 3 you see here, it's automatically assumed to be base 10. So what does this mean to this situation? When you see log 3, you type that in your calculator and that's equal to 0.477. It means exactly what you've seen before, where your base being 10 now, take 10 to the 0.477, and that will equal about 3. And I say about 3 because we rounded 0.477. So you can check this on your calculator and you go 10 and you raise it to the 0.477. It actually goes 1, 2, 1, 2. If you do that, you're going to get something very, very close to 3, like 2.9999999. Okay, so anytime you see log, say log x is equal to y, that's our function. That's the base function we're going to use. So when we see y equals log x, I'm going to show you that here in a minute. That is a function which, you put values in for x, you get values back for y. It's going to create a graph. And so I want to show that graph to you. Okay, so a couple things to point out. First of all, when we have the exponential y is equal 10 to the x, in the last unit, chapter 7, we learned that those functions are like exponential growth. And the growth factor here in this case is 10. It's going to be going through the y-axis at, make sure I'm in the right spot here. That's going to go through the y-axis, the y-intercept at 1. You can check that. So all the stuff that we've done in the past comes back to us here when we start looking at logarithms. Now, I mentioned this at the very beginning, the first part of the videos, that these guys are inverses of one another. Now, you've been long enough in your career here as a math student to know that if you want to look at a function's inverse on a graph, you reflect it across the y equals x line. So let's just put in the y equals x line here. Maybe, there we go. So that represents the green line. And so what we should see then is if we have y equals 10 to the x, that's being the red line there, the exponential growth, and we take y equals x, that's our green line, and we reflect the y equals 10 to the x over that line, y equals x, you're going to get logarithm. So this proves that indeed these guys are inverses of one another. So if I turn on y equals log x, you get this reflection of our exponential. Now there's some key points to look at when we're talking about the log as a function. So we'll point some of those things out. First of all, we have asymptote. We have an asymptote that is the y-axis. So you might make note of that first off. So we have an asymptote. You might want to write this in your notes. This goes, by the way, right along with the example in your book. I believe it's talked about and leads into example number. I'm going to be graphing these things. Example number 5, where we look at the the graph of a logarithm and we identify some key features? Well, first of all, we have an asymptote that is the y-axis. We don't have a y-intercept because it's never going to hit the y-axis. So that's something to consider. No y-intercept. You might write that. So no y-intercept. What's its in behavior? Well, if we do our in behavior, remember you got to look both ways. So as x increases to negative, or excuse me, x goes to negative infinity, f of x, you see there, it's taking off to negative infinity. And they actually say it this way. As x approaches 0 from the left, it's going off to negative infinity. So because we're not actually going into the negative side of it, if you look in the book, and this makes good sense, we better make that adjustment here. We're not actually going to go into the negatives because you can't have negatives input for logarithms. If you think about that, you logic through that, you should see that. So they actually do the in behavior in this way. They modify it and say, well, we're going to approach 0 from the positive side. And we approach 0 from the positive side, it takes off to negative infinity. Okay. Why is that? Think functionally, like put some numbers in there. If you have the function y is equal to log x and you put a value in there for x that is very, very, very close to 0, like say on your calculator, you can type this in log of, let's get really close to 0, 0.000001, let's say. We type that in there. We go log of 0.000001. We get this, -6 going on there. Did I put that 1, 2, 3, 4, 5, 6? Yeah. That would equal -6. So it's going down. It's way down here. The closer I get to 0, the further down the axis it's going to go. All right. So what about when our in behavior goes to the positive? Well, very slowly as it approaches positive, it's slowly growing also, but it'll always take off and keep going up to positive infinity. It's going to take a long time to get to big numbers, but it will eventually get there. All right, so what's your domain? Your domain is going to be, let's write this up here. Your domain can only be the positive reals greater than 0. You can't put 0 in there. Because you think about it. If you try to go, well, what's log of 0? That's the same thing as saying 10, this would be like this. For what value, taking 10 to the y would equal 0. To what power can you take 10 to get 0? You can't. It ain't ever going to happen. So our domain is all values for x greater than or equal to 0. Excuse me, greater than 0. So the domain would be all values x such that x has to be greater than 0. Or all positive reals. That's another way of looking at it. All right, so then what's our range? Well, the range is going to be all reals. All real numbers. Because you get all negatives, and it takes a long time, but it eventually gets out there to all the positives as well. Okay, so there's the analysis of that function. Here's an issue. They're going to ask you to graph these functions, and so I'm going to show you how to do that. And it's really important that when we do this, we create a table. Because if your base is 10, yeah, you can just do it on the right there on the Desmos for you. But you can't type in a Desmos. You will not be able to do this with any calculator, although I never have tried it with Desmos. Maybe Desmos is so amazing that you can. But you can't do the graph on a graphing calculator other than base 10. You can make your own graph. So you got to set up your own table to make it work. Let me get this erased. And I'll show you how that happens. Okay, this is going to be a mess, but you get the idea. All right. So in the book, they're going to ask you something like this. Hey, graph the function y is equal to log base 6, I believe, of x. So functionally, to be able to do that, you're going to have to set up a table of values to make that happen. And so you got to be very strategic about the values that you pick. So you already know that you can't put 0 in there. You can't put any negatives in for x. But you got to be able to use exponential form to be able to evaluate all this. So this is pretty wild. So really, you're going to go 6 to what power of y would give us this x value. So you got to work back and forth to be able to create this graph. And so you might do something like this. Well, what value would I have to raise 6 to get, x to be 1? And I know this is weird, but in other words, log base 6 of 1 would equal what? So again, working back and forth. I know this might be confusing, but you got to stop and think about this. If I want to evaluate 6 as a logarithm's base, I could rewrite it into its exponential form to figure this out. So in other words, 6 to what power would equal 1? Well, it would have to be 0, because any base to the 0 power would equal 1. So one coordinate already we know on this graph is 1, 0. Okay? And now we just keep playing this game. We're just going to keep writing in here and evaluate as we go. I know I just erased that first coordinate, but here we go. All right, so, well, what power of 6 could I get -1? Now, if you stop and think about this, this should make sense. Isn't 6 to the -1 going to be 1/6? So that tells you that you can put in 1/6 into your function for x, and that's going to be the result of -1. So if you think about this now, think about it. Log base 6 of 1/6 would equal -1. It has to. So that means if I go, way down here small, -1/6, that's going to be pretty close to, 1/6, it's going to be pretty close to 0 there. If this is 1, there's 1/2. So 1/6 is going to be down in there. So we're going to go like 1/6, -1. And so you can start to see now that this function is going to go something like that, because I got this key point. I got that value giving us a result of -1 at 1/6. And now you can keep going and go, well, I know that 6 to the second power is going to give me 36, meaning that if I put in 2 to this function, it's going to result in, let me think I did that right, it's going to result in 36. Oh, I'm wrong. That's not true. That's not true. It's more along the other way around. If I take, I don't want to put 2 in there because that's going to be kind of funky. But if I put 2 in for x, it's going to be hard to figure that out. So don't put 2 in for x. What you want to do is put in 36 for x, because that will result in 2. So way out here at 36, so way out there, I'm not going to pull it all the way out there, you will finally get up to 2. And there's 2 right there. So way out there to the right on this graph, way out there, you're going to see where this finally slowly reaches and gets up to 2. It would be out there at 36. Pretty crazy. All right. I guess one thing you can do is try to figure out, well, what value would I have to put in to get to 1? And I'm hoping that you're going to see that right away. In fact, I'm going to erase part of my graph so that it makes sense. Wouldn't it have to be, for us to be able to get an output value of 1 in our, this isn't going to work very well, but let's see what happens here. If I move this up, oh yeah, it doesn't even move up. So my table would go like this. If I want to have an output value of, sorry guys, this is a train wreck. I apologize. Please bear with me. I should have made my table way over here. But let's just redo this. Okay, so we got y is equal to log base 6 of x. What we had so far was, we know that at 1, we're going to be at 0. We know at 1/6, we're going to be at -1. And you should think now, okay, how do I get an output value of 1? Well, that should happen at 6. Log base 6 of 6 should equal 1. Log base 6 of 6 should equal 1. Why? Because 6 to the first power is 6. All I've done, I'm working back and forth between exponential and log form to do this. So now I'm going to go, okay, well, at the value of 6, curl out here, I'm going to finally get to 1. So that backs up what I claimed before, earlier in the video here. It's going to take you a while to get all the way up there to 2, like way out there at 36 to get there. Weird functions, lots of application though in the real world, and we'll see that at some point here. Thanks guys for hanging in there. See you in the next video.